Hello, in this video we talk about hyperbolic functions. It's really a brief introduction to hyperbolic functions. The hyperbolic functions are formed by taking combinations of the exponential function e to the x and e to the negative x. And so I write down below the definition of hyperbolic sine, and it's written as you can see down here, hyperbolic sine x is sinh x, someone might say, and it's e to the x minus e to the negative x divided by 2. And then hyperbolic cosine is e to the x plus e to the negative x divided by 2. And so we have these formulas for hyperbolic sine and hyperbolic cosine explicitly in terms of e to the x and e to the negative x. You sort of maybe could do without the hyperbolic sine and hyperbolic cosine because they're just a linear combination of e to the x and e to the negative x. The hyperbolic functions simply simplify many mathematical expressions and occur frequently in mathematical applications. For example, they are used to compute the tension in a cable suspended by two ends. We also have hyperbolic tangent, which is hyperbolic sine x divided by hyperbolic cosine x. We have hyperbolic cosecant x, which is the reciprocal of hyperbolic sine x, hyperbolic secant x, reciprocal of hyperbolic cosine x, hyperbolic cotangent x, reciprocal of hyperbolic tangent x. And so what we see is that the patterns of identities that we have with trig functions apply here to these hyperbolic functions. Here's a nice little picture out of the textbook, OpenStax.org, the shape of a strand of silk in a spider's web can be described in terms of a hyperbolic function. Did you ever think of that? What type of curve this is? It's not a parabola, it's not a semicircle, it's a hyperbolic function. The same shape applies to a chain or a cable hanging from two supports with its own weight. All right, so we'll talk about that a little bit. So if you had a chain or a cable that's hanging, that can be described in terms of hyperbolic functions. Now what we're going to do here is just apply the definition to evaluate the expressions. So on the side here, I'll rewrite that definition. Hyperbolic cosine x is e to the x plus e to the negative x over 2. So evaluating hyperbolic cosine of 0 is just simply found by plugging in 0 for x. E to the 0 is 1. So we get 2 divided by 2 is equal to 1. So that wasn't that difficult. And then we also have hyperbolic sine x by the definition that I showed above. Is e to the x minus e to the negative x divided by 2. So this is e to the 0 minus e to the negative 0 over 2. That's 1 minus 1 divided by 2, and that's equal to 0 over 2, which is equal to 0. And then finally, hyperbolic tangent of 1. Well, so hyperbolic tangent x is hyperbolic sine x divided by hyperbolic cosine x. Okay, so let's just write this down. So this is going to be sinh 1 divided by cos 1. So that's e to the 1 minus e to the negative 1 over 2 divided by e to the 1 plus e to the negative 1 divided by 2. And so this is going to be e to the minus 1, e to the plus 1, which is just e to the minus 1 over 2, then multiplied by the reciprocal. So we get e minus 1 over e divide by e plus 1 over e. I suppose you could leave it like that, or you could multiply by e to clear the fraction. So this is going to make e squared. When I multiply 1 over e times e, when I multiply e times e, it's e squared. E times 1 over e is 1. I don't know if that's better. It's a little bit better, or maybe not. Anyway, I guess that's what I'm going to do. It's just plugging in. So the question is simplifying. That's better. Okay. I mean, you could spend more time thinking about this. Here's a really important identity. It's sort of I guess you might call it a fundamental identity of the hyperbolic cosine. Okay, so let's go ahead and prove this identity, that hyperbolic cosine squared minus hyperbolic sine squared is equal to 1. So here's our proof. The hyperbolic cosine squared x minus hyperbolic sine squared x is equal to, I'll just put the definition of those function inside here. All right, now I'll expand using binomial expansion. So I get the first term squared, that's e to the x, plus 2 times the first term times the second term. See, I take these two, multiply together, times 2, plus the second term squared. That does it. And then I divide that all by 2 squared, which is 4. Subtract another fraction. The denominator is still 2 squared. Same stuff. E to the x squared minus 2 e to the negative x, or sorry, well, it doesn't matter really, but e to the x, e to the negative x, plus e to the negative x squared, common denominator. So let's see, we have e to the x squared plus 2 e to the x, e to the negative x, plus e to the negative x squared minus e to the x squared, plus 2 e to the x, e to the negative x, minus e to the negative x squared. It's pretty exciting stuff, don't you think? But algebra is so powerful. Let's do it. Let's not give up here. All divided by 2 squared, which is 4. Now we see that there's cancellation here. E to the x squared minus e to the x squared. E to the negative x squared minus e to the negative x squared. And so then we'll get these two guys that are the same, adding them together. 4 e to the x, e to the negative x divided by 4. So that gives e to the x times e to the negative x, but these have the same base, e. So we add the exponents. So that gives e to the 0, which is 1. Yay, proved our identity. The cosh squared x minus sinh squared x is equal to 1. Okay, so have that one. It's a good one. Now, just to remind you, this is what we get with trig functions. We have the identity x, well, I mean, this is by definition of a unit circle that x equals cosine theta, y equals sine theta. And we also have the identity that cosine squared theta plus sine squared theta is equal to 1, which matches, which one comes first? Well, but anyway, if I define x equals cosine theta, y equals sine theta on the unit circle, then if I have a point, which is what we do on the unit circle, if we take this point here being xy, I sort of need more space here. But if I have this point here, xy, where this point here is xy equals cosine theta, sine theta, Too small? I'd say so. So you have a point in the unit circle, which is xy, and that's given by cosine theta sine theta. Okay, and then because it's a circle, we have the identity x squared plus, or the equation of the circle, x squared plus y squared equals 1. But that matches cosine squared theta plus sine squared theta equals 1. Because x is cosine theta, y is sine theta, so x squared plus y squared equals 1 corresponds to the cosine squared theta plus sine squared theta equals 1. That's for trig functions. For hyperbolic functions, we can look at a situation, well, a parameterization really, where we let x equal cosine t, or hyperbolic cosine t. You could do theta, but I'm going to use t. X equal hyperbolic cosine t, y equals hyperbolic sine t. Then we have, as we proved above, hyperbolic cosine squared t minus hyperbolic sine squared t equals 1, which leads us to x squared minus y squared equals 1. Okay, now, x squared minus y squared equals 1, if we put that into Wolfram alpha, we get this graph here. Well, I mean, without inputting in Wolfram alpha, it's still true. This is what a hyperbola looks like. Now, this hyperbola in this equation, x squared minus y squared equals 1, allows x to be negative. But hyperbolic cosine, if you look at what it is, it's e to the x plus e to the negative x over 2 is always positive. So if I just do this parameterization, x equals hyperbolic cosine t, y equals hyperbolic sine t, I get the right branch of the hyperbola. If you get the left branch, you could say x equals negative hyperbolic cosine t. So that sort of ties in why we have that name, hyperbolic cosine, hyperbolic sine, or there's something, it has something to do with hyperbolas, as you see. So you can write parametric equations of a hyperbola using hyperbolic cosine, hyperbolic sine functions as we're doing here. So, okay, got that. The most famous application is the use of hyperbolic, I'll highlight as we go. The most famous application is the use of hyperbolic cosine to describe the shape of a hanging wire. It can be proved that if a heavy, flexible cable, such as telephone or power line, is suspended between 2 points of the same height, then it takes the shape of a curve with an equation called a catenary. The Latin word catenary means chain. All right, so that's a catenary right there. It's y equals c, which is a constant, plus a, another constant, hyperbolic cosine x divided by a. So that's one application. Wow. The Gateway Arc in St. Louis was designed using a hyperbolic cosine function. Well, that's a beautiful place. I think when I was a kid, we drove across the country and passed that. I've never been inside. At St. Louis. St. Louis, Missouri, right? Isn't that in Missouri? Okay. Here we have identities, just the one we have here, hyperbolic cosine x minus hyperbolic sine squared, hyperbolic cosine squared x minus hyperbolic sine squared x equals 1. And then we have these other identities that look sort of like the trig identities. This definitely sinh 2x equals 2 sinh x cos x. That would be the same for trig if we just got rid of the x. But the cos 2x is a little bit different. In trig, it's minus, or for trig functions, minus, but this is hyperbolic sine, and we get positive. So they're just a little bit different, but we'll just keep moving on there. Those are formulas. Definitely, I have no intention of memorizing those. I don't know, maybe someday, but not right now. Okay, the thing that we're going to look at in a calculus class is the derivatives. We have the derivative of hyperbolic sine is hyperbolic cosine. Hyperbolic cosine derivative, hyperbolic sine. And then, actually, this ordering, I don't know why I order it the way I'm ordering. But hyperbolic cosine, hyperbolic sine, hyperbolic tangent, these are very familiar to us because they match the derivatives of the trig functions. However, for the hyperbolic functions, which ones get a negative? Those that have a reciprocal function. The reciprocal functions, derivatives have a negative. Unlike trig functions, the derivatives that have a negative are the cofunctions. So, I mean, notably, the derivative of hyperbolic cosine x is positive sinh x, not negative. So let's just do an aside, although maybe I'll erase it. Note, the derivative of cosine x is equal to negative sine x. See, it's a little different. Hyperbolic cosine. Okay. Now, there are inverse hyperbolic functions, and these have formulas. Notice they involve logarithms. It's not that surprising because hyperbolic sine and hyperbolic cosine are written in terms of e to the x and e to the minus x. Well, the inverse function of e to the x is natural log. So that's surprising. The inverse of hyperbolic would also have natural log. But no showing, I'm not going to show how to find those. And from here we can find derivatives. These actually end up being could be very useful. The derivative of hyperbolic sine x is inverse, is 1 over 1 plus, anyway, you see it right here. These things are hard to say out loud. Hyperbolic sine inverse has derivative 1 over radical 1 plus x squared. Tangent inverse derivative, hyperbolic tangent inverse 1 over 1 minus x squared. Hyperbolic secant, very similar. Those are good ones. Okay, so it's sort of like tangent inverse derivative. Tangent inverse derivative would have a plus here if this were just tangent. It'd be plus, but it's not. And if this were just sine inverse, this would be a minus right there. But that's not what it is it? So that's sort of interesting to look at. And then also this one looks like a good one over here. Anyway, so might use those someday. Let's find the derivative as examples here. So we're going to use two ideas here is that if y equals cos u, then y prime, meaning derivative with respect to x, is sinh u. But using the chain rule times du dx, or times u prime. And so what's u? U is equal to square root of x, which is x to the 1/2. And du dx then is equal to 1/2 x to the minus 1/2, which is 1 over 2 square root of x. Okay, so what I'm doing here is the chain rule. Probably didn't want to write all that stuff down. You just want to jump in and do it. The derivative of cosh, we have written around somewhere on this page, derivative of cosh is sinh. The chain rule says we leave the inside intact, exactly the same. Then we take the derivative of the inside, which is derivative of x to the 1/2. So I have sinh radical x times 1/2 x to the minus 1/2. So that makes sinh radical x divided by 2 radical x. The radical x is locked inside of this sinh, so we're not going to do a funny cancellation. It's not like it's sinh times radical x. You could even take, put parentheses. Sinh has inside of a radical x. Okay, so you can, I sort of did it two different ways. Showing this sort of sideway where I break into pieces, and then I did it not as much breaking into pieces. But the chain rule says you take the derivative of the outside, cosh, and you get sinh, u, and then you multiply by du dx. Well, it's du dx is 1 over 2x. So continue on this side here, same thing though. It's sinh u, but u is radical x, times du dx. So it's sinh u times du dx. So it's the same thing. It's basically the same way. I did it twice. Here we'll also use the chain rule. On the side of the paper, I guess I'll try to remember that if y equals tangent inverse, hyperbolic tangent inverse u, that y prime is 1 over 1 minus u squared. Or is it? Is that right? According to what I wrote down, it is. Okay. And so then I multiply by u prime du dx. All right, so over here I'm going to write y prime equals this derivative. It's not multiplication, it's still chain rule. So it's going to be 1 over 1 minus u squared, but u is sine x. So it's 1 over, so I just put in sine x squared there. And then what's the derivative of sine x? So u is equal to sine x. So we know du dx is equal to cosine x. So we multiply by cosine x. So this is a good one. This is cosine x over 1 minus sine squared x. Do you know the identity? I think you do for 1 minus sine squared x. That's cosine squared x. So this is sort of an aside. I mean, you could take it all the way here. You could write this one, going from up what we have above here, y prime equals 1 over 1 minus u squared is cosine x squared, or no, sorry, sine x squared times cosine x. Okay, so same, just different, a little bit different the way I'm organizing it. Here's another aside we talked about above already. Cosine squared x plus sine squared x, this is trig, equals 1. So therefore cosine squared x equals 1 minus sine squared x. So back up here, this is saying this is cosine x divided by cosine squared x, which is 1 over cosine x, which is secant x. What? Okay, there we did it. Yay. So got that answer. So that's interesting. So it turns out that this is an antiderivative of secant x, huh? Alrighty. I think that's it for the video. You can zoom out a little. But okay. Can't think of anything else to say. All right, goodbye.